Okay, so today's lesson is going to deal with conditional probability for dependent events. So we're going to go ahead and figure out how to find the probability if you're given a certain condition. So over here on the bottom left, we've got this formula, and you would read that the probability of B given, we read that straight line as given, event A has happened. So you're looking for the probability of B given that event A has happened. So there is a formula that says, well, it turns out to be the probability of A and B happening, so the probability of A and B happening at the same time, divided by the probability of A. So an easy way to remember that is that when you're talking about B given A, maybe you could think of this given symbol as like kind of like a divide, that the probability of A goes on the bottom. So let's see if we can write the formula going the other direction. What would be the probability of event A given that event B has happened? Well, if we kind of use that idea that I just talked about, this given condition symbol, put that on the bottom, we would know the probability of B has to be on the bottom. And in the numerator, it would be the probability of both events happening, both A and B. So the probability of A and B. So that's how we would set up the formula. A lot of times you don't need the formula. You can just actually do the probability calculations without it. But that's what the formula looks like for conditional probability. Okay, so here we have a scenario. You're given two boxes with balls numbered 1 through 5. One contains the ball 1, 3, and 5. The other contains 2 and 4. You first pick a box at random, and then you select a ball at random. What is the probability of picking a 2? Okay, so what we want to do is we kind of want to look at this and figure out what's going on. This is kind of like our tree diagram. So over here on the left, we have our two boxes right here. We have box 1 and box 2. So what's going to happen is you're going to pick a box. Well, I can pick box 1. This one's box 1. Or I can pick box 2. If I do that, the probability is 1/2 of picking either box. So 1/2 that I pick box 1, or 1/2 that I pick box 2. Okay, from there, after you've picked a box, there's a probability of picking a ball. Well, the probability of picking a 1 is 1 out of 3 because there's 3 balls in box 1. So this would be 1/3. Probability of picking a 3 would be 1/3. And the probability of picking a 5 would be 1/3. Okay, and then down below it says find the probability of these two balls in box 2 is the probability of picking a 2 is 1/2. And the probability of picking a 4 is 1/2. There's only 2 balls in that box, so it's 50-50 that you're going to get the number 2 or 4. So our question was, what is the probability of picking a 2? So if we follow our chart and we find out where ball 2 is, and we follow the chart, that would go here to here to here. So we're talking about those two probabilities being multiplied together. So that would be 1/2 times 1/2. So what's the probability of picking a 2? It's 1/4. Okay, let's try another one. Let's do what's the probability of picking, I'm going to add this one. This one's not on your paper, picking a 5. Okay, if you come over here to our tree diagram, the probability of picking a 5, well, 5 is in this box. It starts right here. So we're going to go 1/2 times 1/3. We're going to follow that branch. It's going to be 1/2 times 1/3, so that's going to equal 1/6. So the probability of picking a 5 is 1/6. Okay, now we're going to do, let me erase this stuff right here. We're going to do a conditional probability. So I'm going to put a condition on my probability. Okay, so It says, this first one says, find the probability of picking a 3. So we want to pick a 3 given, remember this means given, that you're already in box 1. So if I come over here to box 1, this one was box 1 and this one's box 2, I'm already in box 1, so I don't need this branch over here. I'm already in box 1. What's the probability of picking a 3 given you're in box 1? Well, it's 1/3. So the answer is 1/3. Okay, the next one says, what is the probability of picking a 2 given that you're in box 2? All right, so probability of getting a 2 given that I'm already in box 2. So I'm already in box 2, so the probability of getting a 2 is 1/2. So I don't need all the branches of the tree diagram because there's already a given condition that's been met. And then I'm going to make up another one down here, so one more. It says, what's the probability of getting a 5 given that you're in box 2? Okay, well, if we come over here to box 2, the probability of getting a 5, it looks like to me there is no 5. 5 is up here in box 1. So I guess the probability of getting a 5, given that you're already in box 2, is 0. The number 5 is in box 1, so if my condition is that I'm in box 2, the probability has to be 0. Okay, here's another conditional probability. This time the scenario, instead of a tree diagram, we're given a Venn diagram. Over here on the left, we want to find the probability of B given the probability of A. Okay, if we wanted to do the formula for this, we could say, well, okay, the probability of B given A would look like the probability of A and B divided by the probability of A. Okay, so if we look up here in our Venn diagram, the probability of getting A and B looks like that would be, oops, where's my highlighter? Right here, A and B, that would be the middle part of our Venn diagram. So that fraction, when we look at it, the probability of A would be 0.2, but remember, probability, you have to have the total outcomes. This is what I'm looking for, A and B, out of how many, what's the total outcome? You would have to add 0.1 plus 0.2 plus 0.3 plus 0.4, add all those up, and you get 1. So it's 0.2 divided by 1. And then what's the probability of A? Well, A is the whole circle. Well, that would be 0.1 plus 0.2, so that would be 0.3 out of the total, which is 1. So since they're both over 1, these two kind of cancel each other out, and you end up with 0.2 over 0.3. So if we go ahead and multiply those by 10 to take those decimals out of our fractions, we end up with 2/3. So the probability of B given A is 2/3. Okay, can I do that without the formula? You bet. This is another way to do the same problem without writing out the formula. So what I do to do this one is I say, okay, probability of B given A. So the condition is given A. So what I'm going to do is circle all of A right here. That's all of A. That's my condition. Condition is A. Circle A. That's the condition. Okay, I want, oops, I spelled condition wrong. I want the probability of B. Okay, but you can't use all of circle B. You can only use the part of the circle that's in A. Well, how much is in A? Just this piece right here. So your answer, if you're going to do this without the formula, turns out to be 0.2. So probability, let me write it over here, probability of B given A, just looking at it, is 0.2 out of, what was circle A? 0.3. You get the same answer of 2/3. A lot quicker, a lot faster. than the formula, but it works the same way. Okay, let's go the other direction. Let's take the same Venn diagram and do the same picture. We'll do both ways. We'll do the formula and we'll do without the formula. So probability of A given B would be the probability of A and B divided by the probability of event B. Okay, well, we already know what the probability of A and B is. That's 0.2 over 1. And the probability of event B, well, circle B is 0.5. So that would be 0.5 over 1. So that turns out to be 0.2 over 0.5, which is 2/5. Okay, could we do that same thing without the formula? You bet. So let's write that formula down. We want the probability of A given B. So remember, circle B is the condition. So I'm going to come over here and I'm going to circle B. I'm going to highlight it. Here's circle B. You can only look in circle B. And then what do you want to find the probability? You want to find the probability of A. So in circle B, what part is A? Just this part right here. So your answer is 0.2 out of circle B, which is 0.5. End up with 2/5. Same answer. So you can do the formula, or you can just look at the two circles on the Venn diagram and get the answer. Okay, here's another one of conditional probability. It says, what is the probability that the sum of two die will be greater than 8, given that the first die is a 6? Okay, so if you roll a die, you have a condition. The first die that I roll is a 6. Okay, you're going to roll a second die. Well, what are the possibilities of that second die? Well, there's only 6 possibilities. You can get a 1, a 2, a 3, a 4, a 5, or a 6. Okay, out of those possibilities, how many of them, what is the probability that the sum of the two die will be greater than 8? So how many of those will be greater than 8? 6 plus 1 is 7. 6 plus 2 is 8. 6 plus 3 is 9. 6 plus 4 is 10. 6 plus 5 is 11. And 6 plus 6 is 12. The ones that are greater than 8 are these right here. So that would be 4 out of 6, or 2/3, given that condition already that you rolled a 6. Okay, here's another one. This one is going to prove whether the events are independent. So if you're given a condition and you want to show that it's an independent scenario, then what has to happen is that given the condition, so saying the probability of B given A, that has to turn out to be equal to the probability of just B. Okay, if those two things are equal each other, then you have independent events. Same thing, you could go the other direction. You could say the probability of A given B equals the probability of A. So basically what you're saying is the condition right here doesn't matter. If the condition doesn't matter, then they're independent events. Okay, that's the condition is what makes them dependent. So if the condition doesn't matter, they are independent events. So this first one says a coin is tossed and a single 6-sided die is rolled. Find the probability of landing on the head side of a coin and rolling a 3 on the die. Okay, so we're going to try to do that probability, and we're going to see if these two are independent of each other. So it says, are the two events independent or dependent? How do you know? Okay. Okay, I'm going to go ahead and answer this first question. It says about we're going to find the probability of landing on the head of a coin and then rolling a 3 on the die. So my intuition is that these are independent events that, I mean, we talked about this on an earlier lesson, that flipping a coin, rolling dice, what I get on one has no bearing on the other. So I really think that these are independent. But we're going to go ahead and work through that proof to show you how you can prove that algebraically with the numbers. So if we're going to go ahead and just answer the question, find the probability of landing on the head side of a coin, well, that would be 1/2 times rolling a 3 on the die, that would be 1 out of 6. So that answer is 1/12. That would be the probability. Okay, we're going to try to I think they're independent events. So we're going to prove that. It says, how do you know? So you can use either formula you want. You can use the one on the left, the probability of B given A equals the probability of B, or the probability of A given B equals the probability of A. Doesn't matter. You can pick either one. But what you have to do is you have to define what event A is and what event B is. So I am going to call tossing the coin event A. So the coin toss, we're going to call that event A. We have to know at least which one is which. And then rolling the die, we're going to call event B. So a die is rolled, that's going to be event B. Okay, so if we want to prove if these two things are independent, then if we want to do our probability conditional formula, it would say the probability of B given A. Okay, if we did that formula from a couple slides ago, it would turn, it would turn out to be the probability of A and B divided by the probability of just A. Okay, let's figure out what that is. So the probability of A and B, well, we already answered that question above. That's the probability of tossing the heads and rolling the 3 is 1/12. Okay, the probability of event A. Well, event A is tossing the coin and getting a head, so that probability is 1/2. If you take 1/12 and you divide it by a half, that's the same thing as 1/12 times the reciprocal, and so that's 1/6. Okay, remember, if this is true, then the other half of the statement, remember, here we go, the other half of our independent was probability of B given A equals the probability of event B. It has to be the same. We did this side right here, and we got 1/6. Okay, what's the probability of event B? Well, event B is rolling a die, getting the 3 on the die. Well, what is that probability? That's 1/6. Are they equal? Yes. So are they independent? Yes. Did we prove that? Yes. We kind of thought they were before we started, but we just went ahead and proved that. Okay, this slide has got everything that we've learned in the chapter. It's got the Venn diagram, the tree diagram, a two-way table, the conditional probabilities, just giving them in fraction form. So we're going to take a scenario and we are going to build all of these different ways to represent this scenario. So to begin with, over here in the top left-hand corner is the key, and this is kind of what they're giving you. We didn't get a scenario attached with it like a story, but it looks like to me they're talking about male and female, blue and not blue. So we could say eyes, we could say that's their favorite color. I don't know. We didn't really get a context of what it means. I feel like we'll just go with favorite color. So we'll say, and they're going to let M stand for male, F stand for female, B blue, N not blue. Sometimes you might also see them, instead of doing male, female, you might see it written as male, and then instead of female, they might just say not male. Remember we talked about that idea on the very first slide. I think it was day 1 or day 2, where we talked about that not symbol. So like not blue, instead of writing out the word, they would just put the blue with that little apostrophe at the end. That means not blue, same thing. So you may see it written either way. Okay, so what I like to do, looking over here, first thing they told us is the sample size is 200. So in our two-way table, this is our two-way table right here on the right. So in our two-way table, since they told us the sample size is 200, that means the total of everything is 200. 200 goes in that corner right there. Okay, the other thing they told us was Right here, this means probability of blue. So that means the probability that they like blue. Well, that's 84 out of 200. Here's the blue column. That's a total. So that's going to go 84 out of 200. So out of the male and female, 84 out of 200 like blue. Okay, the next one down below says probability of M. So remember, that stands for probability of male. Okay, well, that's a total. So I'm going to go along the male row, and the total for that would be 64. So we've got 64 right here. Oops. Okay, and now we have a given scenario right here. This one says the probability female given that you like blue, and that's 48 out of 84. So given that you're female and you like blue is 48 out of 84. That's got to be in that column. Okay, so what I would do now is just figure out all the missing spots. So take a minute and figure out what all the missing spots are. Okay, hopefully you got the same numbers I did. Okay, now what we're going to do, before I answer the rest of these questions over here on the left, these questions right here, I'm going to do my Venn diagram. So easiest way to do the Venn diagram is to look at your two-way table. So what I would do in your two-way table is look at this corner right here. This, this corner right here. These are the titles I would use. I would use blue, I would use male, and then I would do 36. So in my Venn diagram, I would pick, let me highlight that here. So this one would be, doesn't matter which one you do is which, but this one I'll put as male, and this one is blue. So that means inside the, and I would write these labels, this is blue and male. That's who we're talking about, blue and male. Both of those scenarios. Okay, so now what you got to do is figure out what are the rest of the labels. Well, if this is male, then this must also be the people who don't like blue, so not blue. And if this is blue, this must be the female. And then on the outside, we have the female and the not blue, the people who don't like blue. So every area should have two labels. If it's a two-way table and you're doing a Venn diagram, everything should have two labels, male and not blue, blue and male, blue, female, female, not blue. I should use every label twice, okay? And then everything is done the way it should be. So now what I'm going to do is I'm going to fill in the numbers. Well, we use this top left-hand corner for a reason because blue and male is 36. So I know the number 36 has to go right here in the middle. This is 36. Okay, this whole circle represents the males. But, and that they're out of, let's see, what's our total? Let's go back to our two-way table. Total males is 64. The whole circle is 64, but I already know 36 of them like the color blue. So you got to take out from your 64, you got to subtract the 36 to get 28. So that whole circle, the part between the 28 and the 36 should add up to 64. Okay, so let's do the other side. Let's do this circle right here. So same thing, this is supposed to be the blue and the female, right? Well, all the people who like blue, that's the blue circle. How do I know it's the blue circle, not the female? Because in this red circle, the word blue appears twice. That's the blue circle. Okay, how many total blue? It was 84. So looking at my two-way table, I see that it was 84. So the total circle should be 84. You already know 36 of that, so that should be 48. That should match your two-way table. Should come over here and match. This column right here. Blue, female, 48. That should match blue, female, 48. Those labels should all match. Everything should match. Okay, so then the only thing we have left, let me erase all these marks here. So this was 36, 48, 84. So the only thing we have left is outside of the Venn diagram, the female and not blue. Well, how many, you could look up here, how many of the female and not blue, so here's female, not blue, would be 88. So that would be 88. Let me just get those off. So 88 would be right here. Okay, so everything looks good. Okay, so to do our tree diagram, you got to break that up into two categories. So I guess I'll start with male and female. And then after you pick a gender, then you have blue and not blue. Over here, same thing, blue, not blue. Okay, so now we got to just fill in what we know. So how many males are there total? There were 64 males. So this line was 64. How many females were there? There was 136. Okay, out of the male side, how many of the males liked blue? That was 36. And how many liked, or not, didn't like blue was 28. Those two numbers, 36 and 28, should add up to be 64, because remember, that's our second characteristic of the male. So down here, female, there's 136. How many of them like blue? The 48. How many of them not blue? The 88. So there's our numbers there on our tree diagram. So then the question is color preference independent of gender? How do you know? Oh, I guess we did know it was color preference because they told us, they're asking us to do that right here. Oh, let's come back over here and finish our, before we answer independent or not, let's answer our three questions over here. So probability, liking blue given that you're female. So the probability that you like blue, so this is blue, that's what the B stands for, given you're female. That's what you're trying to figure out. That's the probability you're doing. So that probability is going to turn out to be 48 out of 136. Okay, down below it says the probability, now this symbol means and, so that means the probability that you're male and, that's our intersection, you like blue. Okay, well, there's 200 people to choose from, and what's the probability they're male and they like blue? That's 36. Now, we probably really should be reducing these fractions as we go, but I'm not, just so you can see how they relate to your two-way tables and your Venn diagram, so you can see those in both of those scenarios. And then the last one, this symbol right here means or. So the probability that you're male or you like blue is what? So probability you're male or you like blue. Well, probability of male is 64 and we like blue is 84. So add those two together. So if we add those two together, we get 64 plus 84 out of the 200. But if you look up here, there's an overlap. We're looking for male or blue. This number right here got counted both times. It got counted in the blue and in the total category. So we're going to have to subtract out the 36, the overlap, and we end up with 112 out of 200. Okay, we're ready to answer our question. Is color preference independent of gender, and how do we know? So we're going to go back to our little formula to prove that. So first of all, you got to pick two events to choose from, and you need to pick two of the events that are kind of not the same category. So what do I mean by that? You need to pick a blue or a not blue. You need to pick one from that category, and then male or female, one from that category. So don't pick male and female, vice versa. Don't pick blue and not blue. You got to pick one from each of the categories. And then you just got to figure out what you want each of those to be. So I'll just let the probability of A equal the event of being male. And then, like I said, and you can pick whatever you want. You could have picked female, blue. I mean, there's lots of combinations here. It'll all work no matter what combination you use. And I'm going to make my event B, be blue, the probability that they like the color blue. So remember our little formula to prove that they're independent. It's the probability of A given B is going to equal the probability of A. So probability of A given B, so let's do this part right here, is the probability of A and B over the probability of B. Okay, so the probability of A and B, so the probability of male and blue is 36 out of 200, but since the next one's going to be out of 200, I'm not going to put them out of 200 because they're going to cancel out anyway. And the probability of liking blue is 84 out of 200. So there we go. That's our first, that's the left-hand side. That's our first ratio, 36 out of 84. And now we're just going to do this one over here, probability of A. What does that equal? Well, probability of A is being male. Well, male is 64 out of 200. So the question is, are these two fractions equal? Or are the decimals pretty close? If you divide them out, not so close. This one is like 0.43 on the left, and this one is 0.32. So what they're saying, if this data is legit, that being the color preference is not independent of the gender. That means there's some kind of relationship between being male and liking the color blue, or being female and liking the color blue, or not liking the color blue. There's some kind of relationship there. Okay, so you're going to be asked to do this on your homework. Fill in this chart, all the different scenarios in your homework. So you can just keep referring back to this example if you need to help you out.